So, good morning, good afternoon, and good evening, wherever you are, and welcome to the online matrix seminar series. I'd like to welcome Professor Terry Tao from UCLA, who will give our very first online seminar. Terry doesn't really need a big introduction. He's one of the most well-known mathematicians in the world, and I recommend you read his Wikipedia page. Before we start, though, for orderly proceedings, we'll present the seminar. And we ask you to put questions in the Q&A section, link under your Zoom. And we apologize in advance that we may not be able to get to all the questions, but we'll try to do so at the end of the talk. I'd like to also thank the sponsors of this seminar series, the Australian National University, Monash University, and the University of Melbourne, and the ASC Centre of Excellence, ASIMS, for making this seminar happen. So without further ado then, I'd like to hand over to Terry.
Okay. Thank you. Yeah, so it's great. It's been a while since I've been back in Australia. It's nice to be back, even if only virtually, but still. Yeah, so I'd like to talk about a very old and popular conjecture called the Collatz conjecture, which is still unsolved, but I managed to make a little bit of progress on it last year, that I'd like to present here. So let me first remind you what this conjecture is. Just some notation first. Oops, I'm sorry. Try that again. Right, so we work with the natural numbers, 0, 1, 2, 3, so forth. So n plus 1 means the positive integers, 1, 2, 3, 4, 5. So the Collatz conjecture is about a certain map that you can iterate on these positive integers. It's called the Collatz map, which I'm going to call Col. And what it does is that you take any number capital N, and if it's even, you divide it by 2. And if it's odd, you instead multiply by 3 and then add 1. So it's a very simple map. It's piecewise linear, piecewise affine. And it either makes the number smaller or bigger, depending on whether you're even or odd. And then you just keep iterating this map. So you take any number n, and you apply this operation. If it's even, divide by 2. If it's odd, multiply by 3, add 1, and then apply it again. That's co-squared, and then again co-cubed, and so forth. And that gives you what's called the Collatz orbit, just the set of all the numbers that you can reach, starting from your original number. And that's some set of natural numbers. So it has a minimal value. So I define the minimal value of this Collatz orbit to just be the smallest element of this orbit. Okay, so just to give you some examples. Okay, so if you start, for example, with 1, 1 is odd, so you multiply by 3 and you add 1 and you get 4. 4 is even, so you divide by 2, you get 2. 2 is even, you divide by 2, you get 1, but you already have 1. So the orbit just cycles back and forth, 1, 4, 2, 1, 4, 2. And so that's the orbit. And so the minimal element of this orbit is 1. Similarly, if you start with 6, 6 is even, it goes down to 3, and then 3 times 3 plus 1 is 10. Then you go down to 5, 5 times 3 plus 1 is 16, and that's even, so you just divide by 2, in fact it's the power 2, so you divide by 2 all the way down to 1 again. And once you reach 1, you again cycle 1, 4, 2, 1, 4, 2 indefinitely, so your orbit is just this set of elements, and again the minimal element of this orbit is 1. If you start with 27, it gets much more complicated. It goes both up and down for quite a while. And in fact, it gets as large as, I think, the largest element is 9,232. But eventually, despite bouncing up and down for quite a while, eventually it does settle down, and it does actually reach 1. And then once it reaches 1, it just cycles over and over again. So again, for this orbit, even though it's quite lengthy, the orbit is still the minimal element is 1. Okay, so the conjecture is that that's actually what happens. So the Collatz conjecture is that given any positive integer, when you iterate, no matter how large you start, it will go up, it will bounce up and down for a while, but it will eventually hit 1. So the minimal value of the Collatz orbit is always 1. So this is known as the Collatz conjecture. It has many, many other names. It's also called the 3x plus 1 problem, because that's what the Collatz map does to odd numbers. It's also called the Syracuse problem, because it was, at one point, a lot of people at Syracuse University worked on it. It's a very well-known problem, and it's an example of what the graph theorist Frank Harari called a mathematical disease. So a mathematical disease is a question, so things like the twin prime conjecture, Goldbach conjecture, these things are all other examples of diseases. A mathematical disease is a mathematical problem which is easy to state, and it must seem to be accessible even to an amateur. And also it must attract lots of solutions, and often, in fact, a single person will think that they're over and over again. Unfortunately, all proposed solutions so far have not worked, have not panned out. So at this point, I'd like to share a nice comic from Randall Munro, who runs the company XKCD, which you may have heard of. And so the comic says that the Collatz conjecture states that if you pick a number and it's even divided by 2, and it's odd multiplied by 3 and add 1, and if you repeat this procedure long enough, eventually your friends will stop calling you to see if you want to hang out. Okay, so this is the Collatz conjecture. Well, that's not exactly the Collatz conjecture, but that was Randall Munro's take on it. So, of course, diseases are very topical these days, so I should briefly review the spread of this disease. So it started in 1937, apparently. So Lothar Collatz, the mathematician, he didn't write a paper on it then, but he was certainly thinking about this problem in the 30s. At least that's what he reports. He first talked about it at the International Congress of Mathematicians in Massachusetts in the 50s. And then it was independently rediscovered by Sir Basil Thwaites. And then around the 50s, it became very popular at various math departments around the world. And lots of people started working on it in like tea rooms and so forth. The first paper on it actually only appeared in 1963, a paper of Terras, we'll actually mention later. And then people started offering prizes for it. So Howard Coxeter offered a $50 prize for it, 50 US. Paul Erdős offered $500 for it. Basil Thwaites offered £1,000. And the number of papers in it kept exploding. So Jeff Ligarius at one point was trying to keep a annotated bibliography of all the papers on the Collatz conjecture. So by 1999, he had tracked 197 papers on the subject. But 10 years later, it had already multiplied to there was over 300 papers on the subject. And at that point, he gave up trying to maintain a bibliography. So after 2012, I can't tell you how many papers there are on this conjecture, but it's been quite popular. I have some quotes of by various people on this conjecture. So the topologist Shizu Kakutani once wrote that for about a month, everyone at Yale worked on this problem with no result. And a similar phenomenon happened when I mentioned it at the University of Chicago. And a joke was made that the problem was part of a conspiracy to slow down mathematical research in the US. Paul Erdős famously said, while offering this prize of, I think, $100, that mathematics is not yet ripe enough for such problems. And even in 2010, Jeff Ligarius was of the opinion that this is an extraordinarily difficult problem, completely out of reach of present-day mathematics. So yeah, it's still out of reach, I think, the full problem. But there are partial results that you can solve, even if the whole problem is impossible. So we can't prove the Collatz conjecture in general, but there are lots of partial results. So first of all, you can test numerically. So in a previous slide, I tested the Collatz conjecture for 1, 6, and 27, and you can just get a computer, and it's actually quite easy to get a computer to test lots of values. And in fact, there was a distributed project called Yo-Yo at Home, where lots of computers donated computer time all over the internet, and they've tested the conjecture as true for all n up to 10 to the 20. So we have a certain amount of numerical evidence. One way the conjecture can fail is if there is a non-trivial cycle. So we've already seen one cycle. If you start with 1 and it cycles 1, 4, 2, 1, 4, 2. If there was any other cycle, if there's any other number n which it cycled back to n without touching 1, then the Collatz conjecture will be false, because that's the minimal value of that orbit will not be 1. We don't know if there are any other cycles, but the best result we know is that any other cycle, if it exists, has to be extremely long. That all other cycles other than this 3-element cycle must have at least 17 million elements. So it's not going to be disproved just by writing down a short cycle. You have to write down an incredibly complicated cycle involving very big numbers. It's also known that the Collatz conjecture is true for quite a few numbers n. So for example, every power of 2, it's obvious that you start with power of 2, you end up in 1. But that's a very sparse set. If you look at all the numbers that solve the conjecture and you count how many there are up to x, then there should be x of them. So we can't prove that, but what we do know is that the number of inputs n up to a given threshold x, which solve this conjecture, does grow at least polynomially. That it's bigger than some constant times x to the 0.84. So a reasonably large set of numbers solve the conjecture. That's known. Although it could still be better than this. It would be great if we could show, for example, that a positive fraction of integers solve this conjecture. We don't know that yet. Here's a nice result by John Conway, who unfortunately actually just passed away a few days ago due to coronavirus, actually. The Collatz map is a map which is piecewise linear or piecewise affine on arithmetic progression. So on the even numbers, it is one linear map. On the odd numbers, it's another linear map. So you could easily try to generalize this conjecture. You could take other piecewise linear maps. Maybe if a number is divisible by 17, you do this. And if it's too much 17, you do that, and so forth. John Conway actually invented, well, he did many things, but he invented, in fact, an entire language, a computer language called FactTran, based on maps like this. And among other things, he could use this language to construct a variant of the Collatz map, so a bit more complicated, with maybe 100 different cases rather than just odd and even. But you do a different linear transformation for each arithmetic progression, and there's a variant of this map and a certain choice of initial starting point where you can't decide whether the orbit. I'm sorry, there's a typo here. You can't decide. You can't decide whether this orbit ever reaches 1 or not. The statement cannot be proved or disproved in the axioms of mathematics. The reason, in fact, is he could encode any Turing machine. Given any Turing machine, you could check whether the question of whether the Turing machine holds or not. You could every Turing machine, that question can be encoded as one of these questions, and there are Turing machines for which the halting is undecidable. So that's a rather remarkable statement. A few years ago, I played with this, and I got some evidence that the problem was hard. That if you assume that the conjecture is true, this Collatz conjecture, it actually implies a statement in number theory about powers of 2 and powers of 3. It implies a certain separation property between powers of 2 and powers of 3, that they move further and further apart as the powers of 2 and powers of 3 get bigger. And in particular, given any fixed difference k, there's at most a finite number of powers of 2 and powers of 3 which differ by k. For example, there's only one pair of powers of 2 and powers of 3 that differ by 1. Actually, there's 2. There's 2 and 3, and there's 8 and 9. But there's no others. I guess also 1 and 2. But there's only a finite number of consecutive powers of 2 and powers of 3. They eventually stop being consecutive, and also they eventually stop being 2 apart, 3 apart, 4 apart. This you can prove actually is a consequence of Collatz conjecture. So any proof of the Collatz conjecture must also prove this statement. Now, this statement is true. We do know how to prove it, but all the known proofs of the statement are hard. Most proofs use something called Baker's theorem, which in transcendence theory, which is quite a non-trivial theorem. It earned Alan Baker the Fields Medal, I think, in the 60s. So this conjecture is at least as hard as certain rather difficult results in number theory. So it's unlikely that there's going to be a very cheap proof of this conjecture. All right. Okay, so the full conjecture is quite hard. So of course, in mathematics, when you can't solve a difficult problem, you try to solve easier ones. So one thing we often do is we try to we look at statistical versions of the question. So instead of trying to prove the Collatz conjecture or some partial version of the Collatz conjecture for every number n, for every input n, you could try to just prove for almost all n. Like all but a 0%, a zero density subset of numbers. And there we can prove more. So one of the first papers on the subject was by Terrasse in 1976, Audrey Terrasse. And what he proved was that for almost all natural numbers n, if you start this map and you iterate it, it is almost always true that you end up with that you eventually reach a number that's smaller than n. So that you eventually go down a little bit. Now, of course, you want to go all the way down to 1. Okay, so this is a fairly weak result. It just says that the orbit would dip a little bit below n. Although one should point out that if you could prove this not just for almost all n, but for if every n other than 1 had the property that the orbit starting from any input dip below, went to something smaller, then you could iterate, and just by the principle of infinite descent, if every number n had a point in the Collatz orbit that was strictly less than n other than 1, then eventually you must go all the way down to 1. So in some sense, Taras almost proved the conjecture, but unfortunately there's a huge gap between almost all and all in this case. So as I said, this result is not really the strongest you could make, because you want to make the minimal orbit go all the way down to 1, and you just made it a little bit less than n. But the result got a little bit better over the years. So a few years later, Alouche managed to show that, in fact, if you start any number n, or almost all numbers n, you get less than n to a certain power, 0.869, as it turned out. So you get a little bit smaller than n, and that exponent was improved a couple of decades later by Collatz to 0.7925, and for a long time that was the best result known. A technical point, these almost, or what does almost all mean? It means that the set of exceptions has what's called zero natural density. That if you let E be the set of all numbers where one of these statements is false, and you count how many numbers are less than x are in this exceptional set, then that number of exceptions should be of lower order growth than x. So when you divide by x, you should go to 0. That's the notation I'm using here. But that's not what, that's a technicality. Let's just think about it like 100% or 99.99% of of all numbers n obey these statements. The way I like to think about this is that the Collatz iteration is like a dynamical system, and another example of a dynamical system is partial differential equations, which is something an area that I work in. And these type of results, that something is true for almost all choices of initial inputs. They have analogs in PDEs. So there are many results in partial differential equations where you take initial data, which is somewhat random. You pick some random initial data, and you want to prove some sort of good control on the solution of such data, but you can only prove it for almost all choices of data. And there are certain results like that, and they're called almost sure local apportionment results, which let you control your solution for a short period of time. Basically, all these three results are basically proven by being able to control the dynamics of this Collatz map almost surely for a short period of time, enough to send the orbit a little bit below n, but not all the way to 1. Okay, so what I was able to prove last year was that I can replace these powers of n, 0.825 and so forth, by any function that grows. So my result says that you can take, if you have any function that grows to infinity, no matter how slowly, then it is in fact true that for almost all, and there's another typo, there should be a capital N here. Okay, for almost all natural numbers n, the Collatz orbit will eventually dip below your chosen growth function f. So for example, I could pick log n. Okay. Number theorists are very fond of iterating log. So this function goes to infinity extremely slowly, and it's almost bounded. I mean, it's very, you have to wait a long time for this to even get above 10. One special case of my theorem is that for almost all numbers n, you'll eventually, if you start with n, the orbit will eventually go below log n. So I can't quite reach 1. I can't even get within a bounded distance of 1, but I can almost do that. I can get within any specified tolerance of distance of 1, as long as the distance is allowed to grow very, very slowly. There is a very small technical point. My notion of almost all is a little bit weaker than the notion that on the previous slide. So in previous work, almost all meant the exceptions had 0 natural density, and I use something called logarithmic density, which is a little bit weaker, but that's a minor technicality, which I will not discuss further. Yeah, so the thing is, in order to get the orbit this small, you have to iterate the Collatz map for much longer periods of time than the previous maps. And those are analogous to results in PD, which are known as almost sure global apportionment results, where you control your dynamics for random choice of data for really long periods of time rather than short periods of time. So that's sort of the difference. It's a global in time result rather than a local in time result. Okay. Let's see, what did I have next? Right. So there are other ways to phrase this theorem. There's a more epsilon delta formulation of this question. So of this result. So another way of stating it is that for every epsilon, there's a constant c such that most numbers most natural numbers end up, when you iterate, less than c. So for example, if you are only interested in what happens to 99% of numbers, epsilon be 0.01. For 99% of numbers, all the Collatz orbits of 99% of all natural numbers will end up bounded by some big constant depending on this epsilon. If you want 99.99% of numbers, you need a bigger constant and so forth. Okay, so this is another version of the theorem, and then there's a corollary. So there's only a finite number of numbers between 1 and c. So just from the Pigeonhole principle, as a corollary, I can tell you that there is some limiting. There is some natural number c naught. Maybe 42 or whatever. There is some special number c naught, such that lots and lots of numbers, lots and lots of inputs of the Collatz map end up at c naught. So that there is some number c naught such that that a positive fraction of all of the orbits end up hitting c naught. Now, I would love to say that c naught is 1. That would tell us that, in fact, the Collatz conjecture is true for a positive fraction of the integers. That would be a great result. Can't I prove that? In principle, you might be able to prove that with a computer now, because I can prove that a positive fraction of numbers will end up hitting some number between 1 and c for some big c. And then so all you need to do in principle is just check the Collatz conjecture is true for all numbers from 1 to c, and then that would imply that a positive fraction of numbers will get sent to 1. Unfortunately, the c that comes out of this argument is probably huge. As we saw, we can only verify this conjecture up to 10 to the 20, and I'm sure it's the c that gets much bigger than that. But in principle, you could do this by finite computation. All right. So for the rest of this talk, I'll talk a little bit about the methods of proof. There's a lot of probability theory and some combinatorics and things that go into it. The first step is to pass to a different version of the question, which is called the Syracuse problem, which is a little bit simpler. And then inspired by this analogy of PDE, so PDEs have this thing called invariant measures. So many PDEs have attached a notion of invariant measure for the data. And we will construct something similar for for this Collatz iteration, something called an almost invariant, or actually almost self-similar, more precisely measure. And this measure is fairly explicit, and it's not too complicated, except there's a component of it which I call the Syracuse measure, which is a little bit complicated, and there's a certain Syracuse measure which I call Sirac. It lives on a cyclic group Z mod 3D and Z, and if you understand how this measure behaves, then you can solve the problem. And after a little bit of analysis, you can it really comes down to understanding the Fourier coefficients, or characteristic function, if you wish, of this measure. This is a probability measure, and this you can write in terms of a problem in probability theory about how certain random walks, whether they are trapped inside certain triangles. And so it actually comes down to a purely geometric problem, which comes down to a basic geometric fact about triangles. So there's sort of a rather strange path to take to prove this conjecture, to prove this result. Okay, so let me talk about some of the things that go into this. All right, so so the Syracuse formulation is you can simplify the Collatz. So the Collatz map has one thing that makes it complicated is it does two things. Okay, so for even numbers it divides by 2, and for odd numbers it multiplies by 3 and add 1. And so the map has this sort of piecewise nature to it, but you can combine the two. You can skip all the even parts of the dynamics and just look what happens to odd numbers. So if you just focus on the odd numbers, which are called 2n plus 1, and if you just jump directly from odd number to odd number, so when you take an odd number, you multiply by 3 and add 1, that'll be even, but you divide by 2 enough times, it'll become odd again. So you can accelerate the Collatz map to what's called the Syracuse map, which is a map from odd numbers to itself. And what it does is that you take any odd number n, you multiply by 3 and you add 1, then it's even. And then you divide by as many powers of 2 as needed to make it odd again. So you divide by 2 to the raise to what's called the 2 valuation of this number 3n plus 1. That's the number of powers of 2 number of times 2 divides 3n plus 1. So if 3n plus 1 was say 12, was say 16, that would be 4. Okay, so this is very closely related to the Collatz map, and the Syracuse orbit is always a subset of the Collatz orbit, and the minimal Syracuse value is always the same as the minimal Collatz orbit. So if you want to prove that the Collatz conjecture, it's the same as saying that starting with any odd number, and if you iterate now the Syracuse map, you always end up at 1. And the main result is equivalent to saying that for almost all odd numbers n, the Syracuse map, it won't necessarily get all the way to 1, but it can get slower than any function of n you wish. For example, less than log n, if you wish. Okay, so this is a minor reformulation of the problem, but it's more convenient because we don't have this splitting of cases into odd and even. Yeah, so the Syracuse map multiplies by 3, adds 1, and then divides by some power of 2. Okay, so now I can at least justify, so I didn't say this before, but there's a pretty widespread belief that the Collatz conjecture is true. So certainly everyone believes the Collatz conjecture is true for all numbers, for almost all numbers n. There is a small minority dissent that some people think that there might be a few very special inputs n for which the conjecture is not true. Like there might be 1 or 2 isolated cycles or some n that goes to infinity. But pretty much everyone believes that at least for almost all n, you imagine n1, or at least to some bounded value. And there is a probabilistic justification for that, which I'm going to describe here. So if you have an odd number, and if you pick it sort of at random, and it's sort of vague, I'm being vague what random means, then of course 3n plus 1 will be even, but often it will be divisible by 4. So about half the time, you pick an odd number n, 3n plus 1 will be divisible by 4 about half the time. About a quarter of the time, we divisible by 8, and so forth. And you can make this a bit more precise. So what this means is that if you look at how many times the power of 2 divides 3n plus 1, if you look at the 2 valuation of 3n plus 1, this is either 1 or 2 or 3. It's a certain number, and you expect it to behave like a random variable, and a certain type of random variable called a geometric random variable, which I call geom of 2. So a geometric random variable is a random variable that takes positive integer values, 1, 2, 3, 4, and it takes the value of each value k is taken with probability 2 to the minus k. So half the time it will be 1, 1/4 of the time it will be 2, and so forth. Let's go to geometric random variable. And we expect somehow these valuations to behave like a geometric random variable. Okay, so remember the Syracuse map is 3n plus 1 divided by 2 to this valuation. Okay, so for n large, I'm just going to ignore this plus 1. And if we believe this valuation is like a geometric random variable, what we see is that every time you apply the Syracuse map, it's like multiplying by 3 and then dividing by 2 raised to a random geometric random variable. Or if you like, if you take logarithms, the log of your output every time you apply your Syracuse map is the log of the input plus log 3 minus log 2 times a certain geometric random variable. So the iteration morally is like a random walk. So every time you iterate from n to Syracuse of n, you should sort of add a certain random shift, which is given by this random variable. And so this is a random walk, and it's got a certain drift. Okay, you can compute the expectation of this random variable. The geometric random variable has a mean of 2, as you can easily work out. So the mean of this is log 3 over 4. And 3 over 4 is negative, so log 3 over 4 is negative. So this random variable has negative drift. And so as you keep iterating, the law of large numbers predicts that you should go down to 0, go down to 1. Okay? Just like if you bet in a casino and the odds are against you, then you're almost surely going to lose it in the long run. Okay, so these are the heuristics that predict why the conjecture should be true. Incidentally, this heuristic also predicts if you replace, for example, 3n plus 1 by 5n plus 1, then the log of 5/4 is now positive, you get positive drift, and now, in fact, the conjecture should be that most orbits should actually go off to infinity. Okay. So just to sort of illustrate this, here I took a random large number, about 2 million, or 27 million, and I just iterated the Syracuse map. So if I multiply by 3, add 1, divide by powers of 2, just keep iterating it. I iterate until it hits 1, and this is a log plot. I took the logarithm of all the iterates, and you can see it looks a little bit like a random walk. If you compare against the drift, okay, so the prediction from the heuristics is that it should trend downwards. The logarithm should trend downwards over time with a slope of log 3/4. And if you look at this random walk, it does generally do that. I mean, with lots of random fluctuations, to be sure, but it does seem to drift down, give or take a Brownian motion. Okay. All right, so that's the heuristic, but that's not rigorous because I didn't say what random means and so forth. And you can ask, can you make this precise? Okay, and you can make a lot of the argument I just said fairly rigorous. You can compute pretty much exactly what the nth iterate of a Syracuse map is, and so you iterate once, you multiply by 3, divide by some power 2, and you add some shift. You do it n times, you multiply by 3 n times, you divide by a certain power of 2, and there'll be a certain shift. So it'll be a certain power 2, and it'll be the sum of n numbers, and each number is the 2 valuation of some portion of the orbit. So there'll be all these valuations, and you will get so the main term will be some power of 3 divided by some power of 2 times n, plus a certain shift, and the shift is something that you can compute. It's some complicated expression of all these valuations. Okay, so what one can show rigorously is that as long as you iterate only for short time, so as long as you only try to control things for times less than a small multiple of log n, let's say 1/10 log n, and you pick n to be, say, uniformly distributed from 1 to a big number x, then you can actually make a lot of the previous heuristics rigorous, that with n drawn at random with this distribution, you can check that all these a's behave like independent copies of the geometric random variable up to a small error, and you can quantify how big the error is. And as long as you're in short times, all the error terms are negligible, and all these a's behave like independent random variables of mean 2. So the law of large numbers suggests, therefore, that the sum of n independent of these n numbers is like n independent copies of random variable of mean 2, and the law of large numbers tells you that this should roughly be 2 times n. And for n large, this offset is very small, and so you're led to the prediction that the nth iterate of the Syracuse map is roughly 3 to the n over 2 to the 2n times n. That's like this red line I drew in that graph a few slides earlier. And so this is something that you can actually establish rigorously for almost all n. So there's a version of the law of large numbers that you can use to establish this. I guess it's called the strong law of large numbers. And if you make little n a small multiple of log n, then so if n is a small multiple of log n, then this is n to 1 minus a small constant, maybe a slightly different constant than this constant here. And so this is basically how you can prove the short time results that I mentioned earlier, that you can get the orbit to go a little bit below, so n to 0.99 or something. You can get a little bit below n in this way. Okay. But unfortunately, this argument stops working for long times. What happens is that in order for this argument to work, you need the number capital N to be uniformly distributed modulo 2 to the little n. And the moment 2 to the little n becomes bigger than capital N, you lose a lot of uniform distribution, and it's no longer the case that all these numbers A1, A2, A3, they no longer behave like independent random variables. So this argument seems to get stuck at just proving polynomial results. Okay, oops. Okay, but a natural thing to do is to try to iterate this argument. So what I've just told you is that if you start for almost all numbers n, if you iterate the Syracuse map, you eventually end up at some value which I call m, which is a little bit smaller than n to 1 minus n to something slightly smaller than 1. Now, you could try to iterate this claim. Okay, so maybe now you just restart the Syracuse iteration starting with m now instead of n. And then maybe the same statement will say that for almost all m, m will iterate to something even smaller, m prime, and m prime is smaller than some small power of m, which is then smaller than even smaller power of n. So if you could concatenate these two statements, then you could boost my previous bound. So I could boost my exponent from 1 minus c to 1 minus c squared. And then I could iterate it to 1 minus c cubed, 1 minus c to the fourth, and eventually I could make my exponent as small as I wish, and maybe that's the way to make progress. But there is a problem, which is that when I say almost all, when I say it's true for almost all n, it's almost all with respect to a uniform measure. So, there's all the numbers from 1 to x, okay, and you take a uniform distribution, you pick n uniformly at random, and there's some small set of exceptions, okay, but outside the small set, we are able to make things smaller. That you can use the Syracuse map to map to a smaller range, like x to 1 minus c, for instance, and then there's a small exceptional set here. And then that will get mapped to everything outside of that small set will get mapped to something smaller than x1 minus c squared and so forth. And this set is small with respect to the uniform measure, as before. But the problem is that the Syracuse map does not preserve the uniform measure. That if you start with a uniform distribution here and you apply this map, what you will find is that when you push forward this probability measure, the output of your Syracuse map will have an irregular distribution. It will not be uniformly distributed on, say, this interval. And in particular, the problem is that it might be really concentrated on the exceptional set that you need to move to the next step. So that the set in which you the exceptional set where things go wrong might be small with respect to the uniform distribution, but it might be large with respect to the new distribution of your Syracuse orbit coming from the previous map. So the problem is that the Syracuse map is biased. That if you start with a uniform number, you chosen number, and you apply the Syracuse map, it does not stay uniformly distributed. And this is what stops us from naively iterating these maps to go further. So the iteration changes the distribution. Okay. So there are several biases that are obvious. That actually, if you think about it, this wasn't obvious to me until I tried to prove. I tried to use this method of proof. But there are biases. Okay, so for example, one obvious bias with this map is that the Syracuse map will never give you a multiple of 3. Okay, so even if n starts off with a multiple of 3, you apply this map, it will never return a multiple of 3, even if it's odd, because 3n plus 1 is never divisible by 3, and you divide by any number of powers of 2, it will still not be divisible by 3. So this map has one very obvious bias. It immediately evacuates all the multiples of 3. And there's a slight variant of this. Actually, it also has some other distortions mod 3 that it turns out that it's twice as likely to be 2 mod 3 than 1 mod 3. And the reason is that geometric random variables are twice as likely to be odd than even. So even after applying one, not just once, you pick up a bias mod 3. It turns out if you iterate 2 times or more, you pick up another bias mod 9, 3 squared, and then you pick up another bias mod 3 cubed, and so forth. So every time you iterate, you accumulate more and more biases, but you only see them modulo powers of 3. So I'll give you some charts to illustrate this. So here what I did is that I took all the odd numbers up to 10,000. And you look at the mod 3, okay? And so if you just take all the numbers from odd numbers 1 to 10,000, and you bin them either the 0 mod 3, 1 mod 3, or 2 mod 3, then they're pretty much equally distributed. So I did a histogram, and so in the dark, in the navy blue bars here, you can see that the numbers n are pretty much equally distributed mod 3. But as soon as you apply even just one application of the Syracuse map, and then you bin that mod 3, then there are no more numbers that are 0 mod 3. About the same number that's 1 mod 3, and about twice as many become 2 mod 3. And so the distribution changes from a uniform distribution to another distribution, and there's actually a theoretical distribution that it converges to. That if you send 10 to the 4 off infinity, it converges to a limiting distribution, which I call the Syracuse distribution on Z mod 3Z. And you can see there's a very good fit between the first iterate already and this limiting distribution. Mod 9 is a similar story. So again, I take all the numbers up to odd numbers 1 to 10,000, and I look at the mod 9. So initially, that's the blue bar. Initially, they're uniformly distributed, mod 9. If you apply one iteration of the Syracuse map, then they're no longer equal to 0, 3, or 6 mod 9 because they're no longer multiples of 3, but they start getting biased. Like they're more likely to be 2, 5, or 8. But then if you apply 2 iterations, there's a secondary bias. It becomes slightly more likely to be 1 and 3, slightly less likely to be 5, and so forth. Okay, so there are certain extra biases mod 9, and again, there's a theoretical limit for what the distribution should be. Okay, and the final bar is something which I call the Syracuse measure on Z mod 9Z. And you can see already by the second iterate, it's a very good convergence to that limiting distribution. So there is a bias, but the bias converges to something predictable. I'll give you a formula for it in just a second. And then finally, this the same picture in mod 27. That again, after iterating, there are biases, but the biases converge to something predictable. Okay, so you can show that that if you just look at what happens mod some power 3, like mod 3, mod 9, mod 27, the distribution of the Syracuse map does jump around a bit, but it does converge to a explicit measure, which then becomes invariant. That once you have that measure, it doesn't change. So there's an invariant measure on the cyclic group, which I call the Syracuse measure, and it's the distribution of a certain random variable. And it's a bit complicated. What you do is that you take n independent copies of the geometric random variable, and you take a certain somewhat complicated combination of all those random variables. So it's rather nonlinear. You know, you take a certain mix. You take partial sums. You raise to power 2. You mix them together, and that gives you some random element, and then of Z mod 3DNZ, and that the distribution of that random variable is the limiting distribution of the dynamics in the cyclic group. Okay, so this you can prove, but that's what happens on the cyclic group. But we're iterating on the natural numbers or the odd numbers. So, but you can use that. So what I did was that you use those measures to propose an invariant measure on the integers. So what you do is that on the numbers 1 to n, from 1 to x, you construct a measure which is biased in a way which is guided by those funny measures that you saw, and I call that measure mu x. And if you construct it correctly, the property that you should have is that if you start with a random number chosen from this distribution and you apply the Syracuse map enough times, you should end up with the corresponding Syracuse measure at a smaller value of x, with a small exceptional set. So there will still be a small number of exceptions where you don't end up with this distribution, you end up somewhere else. But but hopefully you can make the measure of these exceptions small relative to this measure, not the uniform measure. But the point is that you want the same distribution to come out, or a similar distribution to come out on the output as you do for the input. So you want the measure to sort of be invariant. If you can do that, if the measure stays the same, then this obstruction disappears, and then you can iterate this map. Okay, so then once you have this, you iterate to a smaller power, and you iterate to x1 minus c squared, and then x1 minus c cubed, and so forth, and you keep iterating. At every stage, you lose a little bit of mass. Okay, so there's a certain exceptional event at each stage which goes off and does something weird. But it turns out that the total sum of this of the exceptional events behaves like a geometric series, and as long as you cut off at some cutoff which before you reach 1, as long as you cut off at some, like say log x or something, as long as you cut off this iteration procedure before you go all the way down to 1, you can show that the total size of all these exceptions goes to 0 as x goes to infinity. So this is how I can show that almost every number still somehow can follow through and get very, very close to 1. Okay, so all right. Yeah, so this idea, this is not my idea. So this follows a scheme by Jean Bourgain, who used the same idea to control solutions to PDEs. In particular, something called a nonlinear Schrodinger equation for long periods of time. Okay, so I'll clear that and keep moving. All right, so you can compute this, you can work out the strategy, and you run into a slight problem because there isn't just one Syracuse variable, there's a whole sequence of them. So there's one for Z mod 3Z, there's one for Z mod 9Z, one for Z mod 27Z. And in order for this strategy to work, all these measures, all these distributions have to be somehow, they have to stabilize, they have to be compatible with each other. And so there's a certain technical thing that you need, that if you have 2 different cyclic groups, so like you have a small cyclic group, Z mod 3, 3MZ, and a large cyclic group. Okay, and n is bigger than m. So then there's a projection map. You can reduce mod 3 m and map the big cyclic group to a small one. And so you have 2 different measures. Okay, so you have a one Syracuse measure down here and another Syracuse measure here. and they need to be somehow compatible. And the way the compatibility works is that you take the measure here and you pull it back, you stretch it out to a measure here. Basically, every point here gets mapped to a coset, and if you sort of split the mass equally among the equal among the cosets, you get what I call the extension of your smaller Syracuse measure to the bigger one, and that extension needs to be very, very close to the Syracuse measure here. So there has to be a sort of compatibility between these particular random variables, that they have to somehow be close to what's called the total variation distance. So there's a certain technical bound that you need to prove, but it basically says that these maps look more and more similar to each other as Angus bigger. So that the biases, all the new biases, there are fewer and fewer biases that get introduced every time you iterate. So if you okay, so that's what you have to prove. Now, the way you want to prove that, so is that you want to understand that these funny variables. So these variables are given, they look a little bit like random walks. So if I go back a little bit, this random variable is the sum of different terms, and it almost looks like a random walk. A random walk is a sum of independent random variables, and these random variables are not quite independent because they're a couple. Like AN appears everywhere, but they're sort of semi-independent. Like you can split this sum into two pieces, which don't interact too much with each other. So there are these sort of splitting formulas that you can write, for example, the Syracuse map for a big cyclic group in terms of a Syracuse map for a small cyclic group, plus the cyclic Syracuse map for the complementary, the quotient of the two, times a certain shift factor. And this is kind of like saying that the distribution function here is a convolution of the distribution of these two. It's not quite, it's what's called a skew convolution. But convolutions are kind of tractable, that you can control the distribution of a convolution using Fourier analysis. And to cut a long story short, if you want to get this sort of mixing property that you need to get this invariant measure, you need to control Fourier coefficients. So what you end up needing to do is that you need to take this random variable and compute the Fourier coefficients, or what's known as the characteristic function in probability. You raise this to some complex phase, either 2 pi xc over 3 to the n, and all the non-trivial Fourier coefficients, non-trivial means xc is not 0 or not 2 or 3, all the non-trivial coefficients have to be small. And it turns out small means polynomially small. Okay, I'm running out of time. So I guess, all right. So okay, so you have to compute these Fourier coefficients. If this was a random walk, then there's a very standard thing. Then the Fourier coefficients factorize very nicely, and you get a very nice product. It isn't quite a random walk, so it factorizes, it kind of semi-factorizes. So there's a trick, you group these elements into pairs, okay, if you group this up into pairs, then and you rename the pairs to be something else, then it looks a little bit like a random walk. You can set things up so that the contribution of the even shifts look like a random walk, and if you do some standard sort of probabilistic calculations, what you find is that you can make the Fourier coefficients small as long as certain multiples of your frequency are not all trivial. So that so you have your original frequency xc, you multiply by certain powers of 3 and divide by certain powers of 2, and there's a certain random way in which you do this. And if you can make at least some of these shifted frequencies, dilated frequencies, non-trivial, like not close to an integer, then you can make these Fourier coefficients small, and then you can solve your problem. So you have turned the problem into a Fourier analytic problem. But this type of problem you can attack by sort of elementary number theory methods. So all these frequencies are starting from your base frequency multiplied by a power of 3 and a power of 2. So you can just collect all those powers of 3 and powers of 2. So you can start coloring the plane. So for every pair of integers j and k, you can look at your frequency, you multiply by 3 j times or 2j times, divide by 2 a few times. And you can ask, is this number close to an integer or not? And sometimes it is, sometimes it isn't. And then you color the plane this way. So if it's close to an integer, I call it a black point. And if it's not close to an integer, you call it a white point. So the black points are the points where you don't get any cancellation. The white points are where you get some cancellation. And the powers of 2 and powers of 3 that you're multiplying by are given by a certain random walk. And so there's a certain random walk, and you just need to show this random walk doesn't stay entirely in the black zone, that you have a random walk and it hits a certain number of white points. It is entirely black. I'm cheating a lot here, but I'm out of time anyway. So this isn't quite the random walk you pick. There's a subset of this walk called a renewal process that you actually pick. Okay, but what makes this problem tractable is that these black points are actually somewhat computable. So this is sort of easy observation that that if for example, if this number is close to an integer, then if you shift, say, j by 1, if you make j a bit bigger by 1, then this guy will also likely be close to an integer. Okay, like because this number is just 9 times bigger. So if one number is close to an integer, then 9 times that integer is also likely to be also close to an integer. Similarly, if you increment k, then you divide this by 4, and there's a good chance that you will still be close to an integer. So the set of black points is kind of connected in some way. There's lots of big connected components, and in fact, what you can prove just by elementary number theory actually is that the set of black points are arranged as triangles. So the shape of, in fact, what you can show is that, so in this diagram, I've got J and K, okay, and we're asking when a certain power of 3 and a certain power of 2 is close to an integer. And then those ones are black. And it turns out that black points organize themselves very neatly into lots of disjoint black triangles. You can't say where the triangles are. That depends a little bit. That depends a lot on what the frequency is. But no matter what frequency it is, there are black triangles all over the place. And there's a certain random walk which is described by these black dots, red dots. And we're trying to show that this random walk is not entirely contained inside of these black triangles. What you can show with not too much effort is that each of these black triangles turns out to be surrounded by a moat of white. Okay, so what you can show is that every black triangle has around it a certain bounded area thickness set of white points. Okay, and so as a consequence, if your random walk passes, which sort of drifts in this direction, if your random walk passes through a small black triangle, let's say like this. Okay, if it passes through a small black triangle, then it's likely to pass through this moat, and so there'll be a certain number of black points, and then there'll be a white point coming out. So a certain significant fraction of your random walk will be in the right region. So small triangles are not really a problem. The problems are the big triangles, because for a really big triangle, the size of the moat is very small compared to the size of the triangle, and it could be that almost all of your points end up in the black zone, which is a problem. But you can see already here that often, even after you leave this moat, you still often have a lot of white space. And the only time that you're really in strife is if let me use a different color here. The only time you're really in trouble is if oh, that's not a different color. Anyway, is if immediately after leaving one triangle, you end up in another black triangle. Okay, so here, if you exit the big black triangle near the vertex of a new black triangle, then you don't get much time to enjoy. You don't spend much time in the white zone. You end up back in a black zone here. But this particular case is okay because it's a small black triangle, and small triangles are not bad. The danger is if you have a big black triangle like this. Okay, and if there's a bunch of big black triangles here, then potentially your random walk might exit and then immediately end up trapped in another big black triangle, and you'll just never see much white in your path. But there's one final key geometric fact that saves us, is that you see all these black triangles you can prove are disjoint. So if you have two big black triangles sitting above your original black triangle, the tips of these triangles actually have to be rather separate, have to be well separated from each other. They can't be too close, because otherwise the big black triangles will overlap. And so there's a big gap between them. So there's a lot of white space between here. And so many of these maps, many of the random walks will in fact quite often exit the big, each triangle in a big white space far away from all the other black triangles. And because of that, you will usually encounter some cancellation. And that's enough to give you this mixing which gives you this invariant measure, which gives you this result. So you have to do quite a bit of work, more than I expected actually, to prove this result. But I'm out of time, so I will finish now, and I guess we take questions.
Thank you, Terry, and I'll applaud on behalf of everyone. Most people are muted. There's a few questions. I don't know if you can see the questions. Maybe we'll start with the one at the top. Is there any known upper bound on the orbit?
Right. So no. So I mean, there could well be infinite orbits in particular. Okay. So we can't prove or disprove that currently. We don't believe they're infinite orbits. That every single orbit we can numerically test, it ends up at 1. Heuristically, we predict the size of an orbit starting with n should be of size about constant times log n, right? Because there is this drift downwards, right? That it should decay geometrically. So the length should be logarithmic in the size of the orbit, but we can't prove that. Have there been attempts to show independence of ZFC? We don't know. So as I said, John Conway showed that there are variants of this problem which are independent of CFC. And some people believe, I think Conway himself expressed the opinion that maybe the original Collatz conjecture is also independent of CFC. I don't believe so. I believe it's actually true unconditionally. No idea how to prove it, though.
Okay. And the second question is whether you can generalize your theorem to Conway's variance.
That's a great question. Certainly, we can generalize to some variants. So, okay, for example, 3x minus 1 is a 3x plus 1. Certainly, it works. So for I do use a few nice properties of 2 and 3. I mean, not so important. But yeah, this is certainly a future direction of research. I guess the methods can extend to some Collatz type maps, but maybe not all of them. I don't know which.
A third question, the statistical problem. Why is it easier than the original problem?
Well, certainly it can't be harder. If you can prove something's true for all numbers, then you can prove it's true for almost all numbers. But that's the experience that we've seen in other areas of mathematics, ergodic theory, PDEs, and so forth. There are many results that we can't prove always. We prove almost always. For example, Goldbach's conjecture. Every even number is the sum of 2 primes. We can't prove that, but but it's been known for a long time that almost every even number is the sum of 2 primes. The digits of pi are supposed to be uniformly distributed. Almost this is what's called normal. We don't know that, but we know that almost all numbers from 0 to 1 are normal. That you pick a random number from 0 to 1, that almost all numbers have this property. So yeah, once you settle for a statistical result, you can start using lots of mathematics. You can use tools from probability, dynamical systems, ergodic theory. Lots of techniques are in play that are not available if you want to prove something for all numbers.
Right. Okay. Thank you. So there's 2 questions on the Syracuse map. Maybe you can say something about it.
Can searching for a probability measure is invariant help with using the iteration argument? Yeah. So the Syracuse measure is the unique invariant measure for the cyclic groups U1 to 3Z. So I mean, certainly discovering that measure was very helpful for me to find this the correct measure to weight for this iteration argument. Yeah, so in some sense, I found for this particular problem the correct measure. I don't think there's any other measure that's relevant. For more complicated iterations, there might be multiple measures. So this one is somehow uniquely ergodic in some sense, that there's only one invariant measure that shows up. For a more complicated iteration with multiple measures, the situation might be much more complicated. Syracuse measure is not bounded. Why should one bother passing to it? It's not bounded, but it's almost bounded. So there's an exponential tail that sometimes it makes the numbers much, much smaller, but that's a very rare event. It's pretty close to being bounded. But it's simpler because it doesn't branch. Okay, so what makes the Collatz map difficult? Well, one of the things is it branches whether you're even or odd. And the Collatz map, the Syracuse map doesn't have this obvious branching. I mean, it's hidden in this 2 valuation, but technically it's simpler that way. It's easy to see what notion of close to an integer is being used. Yeah, so it's less than I think a certain small power of n. Yeah, so there's a specific threshold. There's less than a certain specific quantity depending on n, and you adjust this parameter to optimize a certain other estimate in an argument. I can look it up, but yeah, it's just some threshold. What part of the proof becomes hard to use natural density instead of logarithmic density? So at one point I have to use a lot of dilation. So I'm always multiplying by 3 and dividing by 2. And logarithmic density is related to the multiplicative Haar measure. It's like the discrete analog of the measure 1 over x on the positive reals. That's the Haar measure for multiplication. It's invariant. If you multiply by 3, it's the same measure by 2. Natural density doesn't have that property. It doesn't behave with respect to dilations. And so there's a technical point where that's needed. It's related to something called Benford's law. Benford's law is like it's like 30% of all numbers start with the digit 1 and so forth. That the Collatz Syracuse iterations, they obey this Benford law. And so actually uniform distribution is not actually a natural distribution to this, because uniform distributions don't quite obey this Benford law. All right. Is there any reason why in the heuristic the iteration seems to sit above the linear decay instead of oscillating around it? Oh, that's just the specific iteration that I picked. Okay, so I just picked one. Okay, so to go back, yeah, I picked one random number. Was the 2738 2791? If you pick a different number, then it will dip below. You know, it's just by coincidence it happened to mostly be above the line. That's just a fluke. Why 3n plus 1? I don't know the specific origin. It's the simplest one for which, you know, if you do anything simpler than 3n plus 1, the question is easy. You can do 3n minus 1. You have almost the same story, except that for 3n minus 1, there's not just one cycle. There's actually 3 cycles. And in the conjecture is everybody ends up with just one cycle. Yeah, 5n plus 1, we believe it goes off infinity. Yeah, but so you can certainly consider other problems, but Collatz started with 3n plus 1, and that's traditionally what we play with. Do you believe the conjecture can be answered during a lifetime? Probably not. I think getting the positive density result is doable. That a positive fraction of numbers is solvable. And I think we can gather more heuristic evidence. Maybe that is true. But yeah, these statistical methods that they don't touch I mean. I don't see, you know, how to exclude that there's some very special choice of initial data which does something very weird. You know, I mean, it would require a very massive conspiracy, but we don't know how to rule it out. Does the heuristic argument fail for any known Collatz type problems? That's a great question, and I would love to know the answer to that. I believe you can. You should be able to construct. Well, I believe that there should be some sort of Collatz type map where most orbits go down to 1, but a very small exceptional set go off to infinity. But I can't. No, I don't know how to construct such a thing. Is it unproven that the 5n plus map has divergent orbits? Yes. We don't know. We suspect it. That I think is harder than the Collatz conjecture. Well, but they're both really hard. The argument I have only works going for maps that go down, maps that sort of get compressed as that get smaller and smaller as you iterate. The argument doesn't work if you iterate upwards, unfortunately. So I don't know how to touch the 5n plus 1 question at all. There's a dynamical system. Yeah, there are many variants of the Collatz conjecture. I'm not familiar with the one about wandering sets. Yeah, there's like a Collatz conjecture for the reals. Yeah, I don't think what I have here relates to that one, but possibly. Yeah, there are certainly there's dozens of variants of the conjecture, and maybe one of them will can be attacked by these methods too. Is there an inverse of the Collatz map? Certainly, yeah, it branches. You know, so there's this picture of this XADC comics. You know, you can see that given any number, often there's more than one number that maps to it. So if you invert the Collatz map, it's multi-valued and it branches out by a tree, and you can start studying the growth of that tree. And in fact, one of the results I mentioned that the fact that the number of solutions grows like a certain power of x was actually proven by investigating the growth properties of that tree. Yeah, so there's certainly literature on it. So there's hundreds of papers on this topic. So pretty much almost any angle of this you could ask has been addressed somewhere. Do you have any result on the period of the Syracuse map? How long it comes to 1? Yeah, so we believe that the time taken to reach 1 is roughly of the power of roughly a multiple of log n, but that's not proven. We know it's at least a constant of log n, but we can't prove that it's at most a constant of log n. And is it advisable to consider the number mod 5 or any other mod prime? Yeah, there's no irregularities in any other prime. I mean, 3 and 2 are the natural moduli because that's what shows up in the Collatz map, right? You know, the numbers 3 and 2 show up in the definition of the Collatz map. So it's not surprising that mod 2 and mod 3 behavior is very important. But 5 doesn't show up, so mod 5 doesn't make an appearance. If you took the 5x plus 1 map, then mod 5 behavior would become important. But yeah, there is no interesting behavior in mod 5. There is an invariant measure, but it's just a uniform measure. Nothing interesting happens. Yeah, all the biases happen in mod 3. Okay. Yeah, so yeah, I mean, yeah, there's the division by 2 will mix up all the residue classes mod 5. And so even if you start with a single residue class mod 5, you quickly sort of spread to all the other ones.
All right. So we've gone through all the questions. Thanks everyone for attending this talk. Thank you, Terry, for giving such an interesting talk on the Collatz conjecture. And I wish you all a very good day or good night if you're going to sleep. Good night, everyone.
All right.
Bye-bye.
All right.